Remember, there's this great algorithm, DPSGD, with privacy amplification and privacy accountants. This is a very good, utility-wise, a very good approach. And this is just a nice schematic by Peter's slides, which tells us that, in every round, basically what we do is sample some gradients, like a batch or maybe a single gradient. We add Gaussian noise. And the way we think of the algorithm is that it releases this in every round. Good. So why not use this algorithm forever? There are a couple of challenges with DPSGD. Both of them have to do with sampling. The first one relates to a question Adria asked in the first part, which is that for our theoretical DP guarantees, we make some sampling assumptions. These are the example we saw in the previous part, which is, for example, that every person is chosen with probability P and added to the data set. This is really hard to manage. People are not always available. You don't always have the whole data set stored, and then you pick whoever you want from there. This also leads to variable batch size. If you actually do this, an expectation is P times N, but it's not always the same. And there are studies that show that the privacy guarantees that we prove are actually they don't hold for the ways that we actually sample in practice. The second challenge still has to do with sampling. And it's, remember when we talked about amplification, privacy amplification by subsampling, we kind of defined a regime for epsilon. I said at some point, if epsilon is smaller than 1, or something like this, then this is the equivalent privacy guarantee. This means that to use the amplification by subsampling lemma, you need to be in a certain regime for epsilon and p, the sampling probability, and the total epsilon that you want to guarantee. This regime, not to go to a ton of details, this is a nice post by Thomas Steinke on differentialprivacy.org. This regime is not, it requires a ton of iterations or more epochs than normal, so it's not really the regime that we operate in practice. So how are we going to avoid this set of drawbacks that comes from sampling, from the requirement of subsampling for DPSGD? And remember, DPSGD without some sampling is either too costly, or privacy amplification results is either adding too much noise, or if you don't subsample, then you're wasting a lot of time in every iteration. OK, so this is the first time we'll switch the way we look at the problem. And we're going to look at this problem through the lens of continual observation. So this was DPSGD, right? The way to look at it now is as follows. In every round, what you're doing is you're computing the next estimate, which if I unroll the DPSGD what's the word? Not induction. Induction. Yeah. You get that the iterate at time t can be written as theta 0, which is the initialization, minus eta times the sum of the gradients of the previous rounds. Right?
Recursion.
Yes.
Recursion was the word?
A Gaussian. What?
You were asking what's the word recursion.
Recursion. Yeah, thank you. Yeah. Exactly. So you unroll the recursion, and you can write the iterate at round t like this. So the first thing to kind of shift your perspective is that I'm not really trying to learn the gradients, right? I'm just trying to learn a good approximation to the theta t in every round. So let's call this a prefix sum, which is the sum of the gradients up till time t. What happens if I instead try to find a good approximation of this sum instead of trying to find a good approximation of each gradient? So essentially, I'm shifting the way I look at the algorithm, and instead of saying, In each round, I have an epsilon delta dp algorithm, which privately computes the gradient, and then it does a post-processing to find the next theta t. Instead, what I'm saying is that in every round, I have an epsilon delta differentially private algorithm, and the theta t is a post-processing of this sum in every round. OK, so and now I can tap into this whole world of differentially private online learning, or essentially learning the prefix sum in a stream. And there's this algorithm called, yeah.
So is it actually the case that I want to approximate that prefix sum? Because that prefix sum is going to have a sequence of theta t's which have used private gradients to get updated.
Yes, that's
I
a good.
actually want to estimate the non-private prefix sum.
That's an excellent point. I'm going to be hiding throughout the fact that this thing is adaptive. So in order to talk about there's a huge point, which is that the theta t's are going into the next gradient and so on and so forth. But yeah, we're not going to think of it like this for now, and maybe we can talk offline about how you reintroduce the adaptivity of good, thanks. Very insightful. So if my problem is this now, I have an input, it's a stream, G1 to GT. Every person is one of these gradients. And then what I want is to output in every step the sum of the gradients so far, the sum of the G's so far. How can I do this differentially privately? So the binary tree mechanism does the following. You construct a tree, a binary tree, with these nodes, and these are not noised or anything. This is just, S4, 5 is just the sum of gradients 4 and 5. S of 0, 3 is the sum of, well, this is from 0, the other one's from 1, but the sum of gradients 0, 1, 2, and 3. Okay? So this is a binary tree where I'm storing prefix sums, and the leaves are just the gradients themselves. Okay, so what I'm going to try to do is maintain a private version. And you can think that each one of those nodes has noise that's represented by V, A, B, and it's Gaussian noise, d-dimensional, with variance sigma squared in every direction. Good. So this is the big idea. Every one of those GTs, so every person, every gradient that's being added in the stream, can affect a limited number of nodes in that tree. In particular, when I add G6, the nodes that I need to change, the nodes that are going to change, are only the parents, like S6, 7, oh no, S4, 7, and S0, 7. Right. So each person affects at most log t, or log capital T, of the points that I'm maintaining. So this means that the noise I need to add to each of those nodes scales with log t, not t. And now the algorithm, whenever they get a new point gt, they're going to add it to the tree, basically updating the parents. And then they're going to output the partial sum at this step. And how do I output the partial sum at this step? If I have this tree, how do I compute, for example, the sum of the first 6 gradients? I add the purple circles from there. So I just add S0 to 3 plus S4 to 5 plus G6. So the next big observation is that every one of those partial sums decomposes into, at most, again, log t nodes from this tree. So this is the example. If I want to output a noisy version of S0 to 6, then I need to add these 3 nodes. And these 3 nodes are the non-private sum, which breaks down into the sum from 0 to 6, plus the noise, 3 independent Gaussian noise random variables. Good. So what this means is that my error for every one of those STs is basically the sum of log t independent d-dimensional Gaussians, which again scales with log t. So what this whole thing means is that the error of the partial sums due to privacy scales with log. Now I have a kind of a loose analysis here, but it scales with log to the 1.5t, which, let's go back to the gradients. If you were to add independent noise to each one of the gradients and then say, okay, the partial sum is the sum of the noisy gradients, then what you have is the sum of the gradients without privacy plus t of those independent d-dimensional Gaussians. So this is kind of revolutionary because it gives you a log t error for the partial sum in comparison to the independent noise that we saw before. Okay? So you might say, okay, how do I use this? And we're going to look at differentially private FTRL, follow the regularized leader. These were one of the first works that showed that talked about differentially private online learning and did follow the approximate leader. But the high-level outline of this algorithm is, again, you initialized theta 0, and in every round, you compute the partial sum privately through the binary tree mechanism. And then you do the update step, which is a follow the regularized leader step. But if theta is unconstrained, then you go back to this dPSGD step, which is essentially in theta 0 minus eta times the partial sum, the noisy partial sum. So why is this great? It's great because now the excess risk, this L of theta bar theta minus L theta star, depends on the error that the binary tree mechanism gives you. And without going into details into like how this decomposes, it overall, if you choose eta and t appropriately, like we did before, it overall gives you an error that scales with d to the 1 over 4 over square root epsilon n. Remember, dPSGD, when we chose eta and t to minimize the total error, gives you this instead. So yeah, what did I do? Oh, yeah. So like epsilon is outside, epsilon n is outside the square root. Thank you. But the point of this is to say, we switched the way we looked at the same algorithm, and we said, let's think about it as releasing partial sums. And so maybe this opens up a new space of algorithms for this problem, on which we can build on even more and have even better results. And we'll dig into this right now, unless there are questions. Okay, this is good. I'm going to move on, since you didn't have any burning ones. No. Yes.
The same pattern you're using, you were not using the excess risk before. I think you've switched the...
I did the error guarantee?
Yeah, were you using excess risk before, or?
I was using the loss of the average iterate. Right? This is not the one? Yeah, like, which is, so you could say it's either the sum of the average of the loss on every data point, or if it's convex, just the loss on the average iterate. Okay, good. So what we did, again, was look at this algorithm. It's the same type of algorithm, but we looked at it in a different way. We looked at it through this sort of partial or like prefix sums way. And notice that what we kind of, like this is an intuition slide, what we kind of observed is that the binary tree mechanism, the noise it adds to every one of the partial sums is not independent anymore, right? So you maintain the binary tree, and then to compute each one of the partial sums in every round, you add some of the nodes of the tree that you're maintaining. So essentially, all these z's in every round are a combination or some choice of the independent noise that you've added to each of the nodes in the big tree. So these are not independent between themselves. And one way people talk about this to give some intuition is that you're essentially using this fact to cancel out noise as you go. So here comes the second switch in the way we look at the problem. So the first switch was what? That the problem is essentially a continual observation problem, like you're trying to release the prefix sums. Now the second switch is that prefix sums are themselves linear queries. So why do I say this? Let's think about the matrix of the gradients. So that's a stack of all the gradients. Row 1 is the first gradient. Row 2 is the second gradient. So it's a n rows times d columns matrix. OK, these are the gradients. Now, you can define a pre or a prefix, which is a lower triangular matrix. It's defined like this. So the lower triangle is ones, the other is zeros. So essentially, first row has only the first point is 1. Second row, the first two coordinates are 1, and so on and so forth. Now, the prefix sums that you're trying to release are this matrix. So the first row of this matrix S is the first row of the prefix matrix A times G. So that's only G1. The second row is G1 plus G2. The third row is G1 plus G2 plus G3, and so on and so forth. So this is, again, a stack of the vectors of the prefix sums. Yes? No? OK. Good. So what we want to do is release the prefix sums, like this whole vector privately, this whole matrix, sorry, privately. And this, again, opens a whole other literature in differential privacy, which is the literature where we're trying to release linear queries. And there have been a lot of works in this literature. A couple of those have something called the matrix mechanism or the factorization mechanism. And this is what we're going to call correlated noise mechanisms. And they go like this. Again, our goal is to compute S, which is given A and G is we're multiplying these two matrices. The inputs are G, and you can think of this as each gradient is a user, and so you have n users. And we call A the workload matrix. So it tells you what queries you want to compute on this input G. And now, so the strategy of these factorization mechanisms is the following. First, you're going to pick a factorization of A into two matrices, B and C. I think it's better to think of these as square matrices. So like A is an n times n matrix, B and C are also n times n matrices. Then what you're going to do is get this input G and add correlated noise to the matrix. So this means you have noise Z, which is independent Gaussian noise. So it's an n times n matrix. There's an independent 0 sigma squared random variable in each of one of those. So you you create this matrix, this Z matrix, which is independent, but then you use C, or the inverse in C, to essentially create like correlated noise. Okay. And so at the end, you're releasing A times G plus C minus 1Z, which, if we break it down again, A times G is the thing you wanted to compute, right? And A times C to the minus 1 times Z is B times Z. It's a very general framework. So again, what do I want? I want to compute A times G. What do? I break down matrix A into B and C. I add correlated noise to G, and I output this. Okay. Yes?
So compared to DPSGD,
Uh-huh.
what has changed is only the noise addition mechanism, right? If the release has not changed, we are still releasing all those intermediate steps, right? At every
Yes,
time.
that's correct.
We are just making the noise correlated.
Yeah, exactly.
So I'm wondering what happens if we decide to just release the final model parameter at capital.
This is an excellent direction, and we're going to mention a little bit about it at the very end. Yeah. Okay, this is the framework. Let's try to talk through, whoops, wait. Oh no, okay. Let's try to talk through this framework in terms of privacy and accuracy. So privacy. This is again a part where I'm lying in a little bit because of the adaptivity discussion. But aside from this, this is the output, right? A times G plus C to the minus 1Z. We write it that way, and so it's a post-processing of the thing in the parentheses, right? So I need to argue that this is private, and if that happens, then the whole mechanism is private. And so now the noise I need to add to make this private turns out to scale with the column norm of C, which is basically out of the columns of C, which one has the biggest L2 norm? That's the one. So the maximum L2 norm of any column in C. So the sensitivity of this thing here depends on C. And so the noise I need to add, so the sigma that every one of those coordinates is going to have to scale with this column norm of C. This is kind of expected, right? Like, I expect that G is going to change by roughly 1. I've bounded the gradients so that they have L2 norm 1. So the question is how much multiplying it with C stretch or shrink any one of those points. And so the column norm of C comes in. Good. OK, so to guarantee differential privacy, the noise I need to add scales with the maximum L2 norm of any column in C. In terms of accuracy now, what I'm releasing is, let's go back to this line. Oh, OK, you see it. Is the prefix sums plus B times Z. So what is the noise, the error of this mechanism? It's B times Z. And so if I want to estimate, to compute the, for each one of those prefix sums, the worst error that I'm going to get in L2 norm, then this depends on the maximum L2 norm of any row in B now. And of course, that's multiplied with the variance of the noise, which is Z here. And so it also scales with D sigma squared. The punchline, without looking at like the specific norms here and how we compute it, is that in order to guarantee privacy, you need noise variance that scales with the column norm of C. And then the utility is going to scale with both the column norm of C, but also the row norm of B. Again, we're in a very generic framework, and this is the guarantee that you get. Now, going back to dPSGD, can we put dPSGD into this framework? And essentially what we do is add to the G's, we're adding this correlated noise. And you can imagine we're releasing the partial sums, but in this case, it's the partial sums minus eta times the partial sum plus theta 0. But we can frame SGD as a factorization mechanism if we choose C to be the identity matrix. So the noise is not correlated, right? So in every round, basically this is the C to the minus 1, t comma tau is 1 only for t. So this is only one ZT independent Gaussian noise, d-dimensional vector. So if I go through the framework that we just talked about, C is the identity. This means that B must be the prefix sum matrix. The noise I need to add is going to scale with the column norm of C, which, again, for the identity matrix, each column has at most 1, 1. So the L2 norm is 1. And these are the prefix sums. And the error I'm going to get depends on the row norm of B, which is, unfortunately, square root of n. Why is that? B is the lower triangular matrix. So one of its rows is all ones. So the L2 norm of that is square root n. So this means that the max noise error in one iteration is going to be square root n. At the same time, it's pretty fast because in every round I'm computing an independent d-dimensional noise, and I'm only storing that vector in that round. Good. Let's put more things into that framework. This was dPSGD. Another way to think about it is input perturbation. There's output perturbation, where you're adding independent noise to only the partial sum at the end of each round. And now this would mean that C is the same as A, B is the identity, and so the noise you need to add in each round scales with square root n, and again, you'd get the same utility. Let's go to another more interesting example, the binary tree mechanism. So in the binary tree mechanism, the C and B matrix. So what is the C and B matrix again, right? C is the one that tells you which noises you're going to add in every round, the correlation of the noise, right? And B is telling you the output. What is the output? How are you going to compute the output for that round? So both of these cases, if you remember, these matrices were log n sparse. So you have only log n noises that you're adding in every round. And every prefix sum only depends on log n things. So this actually gives you an excellent utility, because both the row norm of B and the column norm of C are square root log n. And so the utility you get scales with log n. The running time is roughly d log n, and the memory is roughly d log n. So this is much, much better than the other two approaches, right? And that's one way to look at it, through the factorization mechanisms approach. Now you might ask, okay, can I just find the best C and B for my A? And you can. And here is where a whole other world of research starts, where essentially, I guess the thing to say is you can find the best C if you solve this problem. And imagine you had the best C and you had it stored in memory somewhere. For prefix sum specifically, the error that you would get would scale with something like 1 over pi natural logarithm of n. This is a non-constructive upper bound, because actually this minimization problem has a very specific solution, the gamma 2 norm of matrix A. And so you can non-constructively show that this is the best you can do for this problem, the best error. And there are also lower bounds that show this for Gaussian mechanisms. So let me sum this up by just saying you can find the best matrix C and B as a result. And the best you can do is this utility 1 over pi times ln of n. But of course, the running time would be roughly d times n. So in every round, you need to compute the multiplication of the matrices, C times Z. So that's d times n. And also, you need to store the matrix C and store the noise, the d-dimensional noise in every round. OK, that's good. I would say, like normally, I would say this sounds like we're done, because the binary tree mechanism gave you a d log n memory and time, and utility was base 2 log of n plus something small. So I would say that we're done, but we are not, because this is 4 times 4.5, it seems, times higher than this bound over here. And also, again, you would say, OK, maybe that's fine. But it's not if you actually want to use these algorithms in practice. So a whole bunch of research with really interesting math, actually, comes in to try to fill this gap. So again, what is the gap? You want this utility, not log base 2 of n, 1 over pi log base e, like natural logarithm of n, with a better running time and memory per round. And just to kind of briefly tell you what this looks like, the next step was to impose, instead of a lower triangular matrix structure, impose a toplet structure, which means that instead of having to find this n squared over 2 different parameters for C, or store n squared over 2 different parameters for C, toplet matrices have the structure, which means that every diagonal has the same, is the same. Every member in each of the diagonals is the same. So you only need to store n of those parameters and not n squared. So that's one improvement that we got. Let me wrap this up. And so there were many more approaches to this. So the banded toplet matrix even tries to reduce this number by even more by saying, OK, I'm going to assume that whole bands have the same parameters. And so this means that instead of n, I need to store even fewer things. But we're still kind of in the realm where this is d times n, this is d plus n. Remember, the binary tree mechanism had d log n. in both time and memory per round. The final news from this world is that the so-called BLT structure, or buffered linear Toeplitz structure, is a matrix that kind of looks like this, but D is not what you think it is, so don't look at this picture very hard. But it gives you very close to the optimal in all three aspects. So the utility is optimal, the running time is d log n, d log squared n, and the memory is also the same. So it's almost as time and memory efficient as the binary tree mechanism, but it gets you the 1 over pi natural logarithm of n utility instead of log base 2. I really like it when people write things, and I shouldn't say should, but I think it's nice when people write surveys and blog posts and things like that. This is a very nice survey that talks about all of these types of correlated noise mechanisms, tries to put those in the same framework again, and talks about the optimizations that go into these results where you try to get both the absolute best utility and memory and running time. Pause for questions.
I was just curious, these guarantees are in a toy model, right? It's a convex bounded gradient model, and you're tuning the step size using problem-dependent parameters. In practice, you're applying it to a non-convex problem, tuning the step size heuristically. So, do you actually see a gap between binary tree and the other approaches in practice? Is that the reason to?
I would not expect to, but I would say that the fact that all these people decided to spend time on this was, important. It seems. I think the last 3 years there have been quite a lot of papers, even more, maybe, 3 years, on improving even just constant. So, and I think it's also quite interesting. Like, for example, I think a rational approximation of the square root of 1 minus x turns out to be like a really important thing to look at and try to figure out. So, I think there's really interesting connections to approximation theory and really hard math. And I guess my intuition is that if someone is willing to do that, it's probably something that has impact. You could do it for fun, of course, but too many people working on it. It's a signal, I think. Yeah.
Can I just chime in? I run the group that 4 of those people are part of. We do care a lot about those small gaps, because the difference between the BLT in practice and the early iterations that were practical, which is really the DPSGD family and DPFGL family, results in really meaningful utility differences after optimization when you're training large models.
I think my question is more like, is this toy model indicative of those practical improvements? Because here you're assuming lots of things, tuning step size in a very particular way and all of those things. You're saying this is still indicative of?
Yeah, the improvements
like
in this series resulted in real differences.
Okay, the 4.5 times factor is actually.
Yeah.
Okay, that's very interesting.
The total square measure is a good proxy, if that's the question.
Right, that's what I was going to say. Yeah. Go ahead, Peter.
No, that's it, I said.
I'm not sure everybody here agreed.
Yeah, so looking at the total squared error across all the iterates tends to be a very good proxy. So it allows you to do very elegant math, and then it translates into practice, which is really nice.
And I don't know if there's, I think there's another algorithm that also gets you d log n, but this is, instead of 1 over pi, something like has a 1.01 in front of it, so not good enough. There's probably a bit more space here, but you have to be willing to look at the papers in detail, which are really interesting, but quite complicated. Good.
I have one more
Yes.
question, which is my previous question. So,
What was the previous question?
how does the optimization work out with these? So, if you do this correlated noise mechanisms and everything else, then how does the optimization analysis work out? Because you have this propagating
You mean the
errors. over-
privacy analysis or the?
Yeah, in the private setting, like the optimization term that you get using whatever algorithm you're using, how does the propagation of error? Because in this tree that you drew, it is true that you're only calculating those prefixes, but the noise that they generate will change the model, which might change somewhere else in the tree, something else, someone else computing another gradient. It's very weird.
Yeah, I think the only reason this works is because it's Gaussian noise, but yeah, there's a nice lemma that translates from one thing to another, like from the adaptive to the non-adaptive. It's really nice, but yeah, we'd have to like it. I totally hit this in this talk. And of course, it's not always true. It's specifically true for the Gaussian noise that we're adding.
Yeah.
And I can point.
Maybe I
yeah.
can just add some, like at this point, I think there's sort of somewhat more general results than that
Nice.
statement. But
Like what more than
that,
Gaussian?
a number of sort of privacy notions have this sort of, like Gaussian DP and CDP and stuff have this kind
So
of.
it is still Gaussian. related.
Yeah, I mean, it's not everything, but there's still some, like a number of sort of more general results. Anyway, the short version is that you need like a non-trivial additional reasoning, even though every single natural algorithm we know has, like, basically is it's easy to show it's non-adaptively private and that analysis carries over to the adaptive setting. But we know of like artificial examples, both of underlying problems and specific algorithms that exhibit differences between these definitions.
What do you mean by non-adaptive and adaptive? I don't think I understand.
The same difference that you're trying to point
we can
out,
talk
right?
about it offline.
I think I'm just thinking of some error propagation. Like, there's no error correction happening here.
Oh.
That's the thing I'm concerned about, the
Oh, the
optimization.
error propagation. No, interestingly, yeah, so that's hidden in the analysis, but actually, in some sense, the gradient descent kind of takes care of that. So the short version is that,
Is it
like, this is not how the math looks, but intuitively what's going on is even if you drift, because you're computing your gradient wherever you happen to have drifted to, and then adding that gradient in, it pulls you in the correct direction.
Okay. Does this all still require bounded gradient assumption? Is that why
Yeah.
it's all working out? And
Everything is
Oh
like
yeah,
for
there's still
bounded gradients,
bounding
yeah.
of some kind, or gradient clipping going on.
Under that, I can believe that because
Anyway,
Yeah.
sorry, I don't want to take.
But yeah, that's all the discussion is. Yeah. So like, okay. Let me think. So there are a bunch of things we didn't talk about. One thing is clipping. Another thing is this setup that every user comes in a stream, or like, it doesn't have to be a stream, but the point is that every user shows up once. This is obviously not true. The network data setting that Adam briefly mentioned, maybe we'll get back to this at the end. But the disclaimer is that there are a lot of other things that go into it that we didn't talk about. But I want to highlight some of those things or some of those questions. Some of them came up in your questions, so I think it's nice to talk about them. Okay, one direction that I really like is this last iterate advantage kind of research. Bless you. So the idea is the following. you don't really have to, like the way we've been talking about these algorithms is as if you're releasing in every round something, right? Either the gradient or the prefix sum. This doesn't have to be the case. You're releasing only the last thing. Of course, usually the algorithm sometimes, or I don't know if it's usually, but they might be releasing the average of all the rounds, which is not the last thing. But let's assume you're only releasing the last thing. A natural question is, can I gain something from that? And there's both in practice, like empirically, it looks like it should be the case. But also there's really nice theory that tries to argue about this, and argue that the fact that you're hiding the state of the algorithm should help. One nice result, one of the early results that I like by Altshuler and Talwar basically says that if you have convexity, by the way, which is also important for this type of result, your privacy loss stops growing after a while. So you grow, your privacy loss grows after a few rounds, but then it plateaus. And so this is a really nice type of result. It tells you can keep training as much as you want. But theoretically, these results require some assumptions. And so it's hard, we have to work harder on them to see like if they could work for non-convex things or average iterates or things like that. A natural other question to ask is, okay, optimization people would go, what about second order methods? Why are you guys so fixated on first order methods? Well, I mean, all the things we talked about in correlated noise mechanisms can apply to weighted linear queries, which would translate to like a momentum or accelerated gradient descent type of thing, but not second order. And there is a work that tries to do second order methods, and I think it's a really promising direction. But I've taken permission to say this, but Madi can disagree. I guess the takeaway is that the privacy budget you need to consume in order to learn higher order information actually takes away a lot from your utility. And so even though you're using a second order method, which might be better, you perform not better than DPHGD with amplification or other methods. A whole aspect that we didn't talk about is, of course, the public data aspect. I don't think anyone does this thing that I said with just like the private data set only. I think the idea is you use public data, you train a big model, you're in a good shape, you have like a theta 0 that's really good, and then you might use the private data for fine-tuning or to continue training on the private data. And there are even some theoretical ideas that say, it's just, there are separations that say like you'd never achieve the same utility only with private data. There are other approaches to think about. It's not just like I'm training and I get a good starting point and then I use private data for the rest of the training. It's I use public data to get some useful information about my data and then try to use this information in another algorithm. And there are really nice works that even show like that if you use even linear regression, but you've handcrafted, you've picked the right features using public data, then you can do actually pretty well in comparison to a more complex model. So using public data can really save you a lot of utility. This other work by Peter et al., which says, okay, let's use public data to find a lower dimensional subspace where our gradients might lie, and so I can use much less noise and memory and running time if I work in a lower dimensional subspace. And there's also earlier works that started using public data through this teacher-student model that were really a milestone as well.
Well, the papers in that section show those comparisons all on private models?
Yes.
On the private setting specifically?
all of those are on private bottles, yes. That's right. Okay, I think I should leave Adam 4 minutes. And as I'm walking down and he's setting up, I'm just going to tell you what the other slide deck, which was 40 minutes, was about. Okay, so I think the idea is that a bunch of us work in private statistics, and not to brag, but in private statistics, we have a bunch of ways to deal with unbounded data. So we don't have to clip our data anymore, guys. We sort of compute things with respect to higher order, with respect to covariance, even if we don't know the covariance, and we don't spend privacy budget or utility to learn the covariance. So okay, I guess what I'm trying to say is that in private statistics, there are many works that try to look at adaptive analyses, where the error kind of scales with the is smaller for easier. Which one?
You keep talking into the microphone.
The error is smaller for when your data is easier, and your algorithms adapt to that. And it's a really interesting, I think, question to see if we can do this for, this type of learning as well.
Right. So I'll just say there's a really nice subfield that we were hoping to cover in this tutorial, at least a little bit of, which is sort of looking at the theory of how to design differentially private algorithms for these high-dimensional statistical estimation problems. And this is something that Lydia's done a lot of work, really nice work on. And the reason it's relevant, in addition to just being interesting on its own, I think in terms of even in terms of high, large-scale learning and the kinds of problems that say you face when training large language models, these statistical estimation problems are a really nice playground for developing new algorithmic ideas that allow us to go beyond potentially the kinds of straightforward-ish first-order methods that have so far been most successful. And so I think they're worth kind of taking a look at if this is an area you're interested in knowing more about. And in particular, there's some really beautiful connections, as Lydia was hinting at, to the theory of robust statistics and algorithmic robustness. And so there's a lot to be said there. That said, I'll just talk briefly, just to wrap up. So the program is on federated learning. And so far, everything we've been saying really is kind of looking at this setting of sort of the classical single learner, single data set, one contribution per person setting. And so I'll just give you a flavor of the differences that come up, and we won't by any means do justice to it, but hopefully give just a little bit of a sense of what's going on. So when we talk about federated settings, what are the things that change relative to the more standard settings we've been talking about so far? Well, the data can reside in lots of places. That's usually what we mean by federated, although there's sort of approximately as many meanings of federated learning as there are people who use the term. But now when we start thinking about privacy, things can get weird, right? So just to give you a small sense of what can go wrong, what can change. Okay, if I'm looking at one person's data, so Alice's data may kind of sort of the place where Alice's data lives may correspond to this data split in the sense that, oh, that's not, where do I get a laser pointer? I do, yeah. So for example, it could be that data set X2 is Alice's data set and is X2 is Alice's phone, and so all that data is her and about her, and that's where all of her data lives in the system. But it could also be spread across all sorts of different places. And then outputs can also be complicated. I could be producing, one model, but I could be producing many different models, perhaps over time, or perhaps over space, right? I could be solving many different related learning problems in each one of these data sets could correspond to a different distribution, different problem. Maybe they're overlap, maybe they don't. So often, this is often formalized via some kind of multitask learning setup. But the kind of main point I want to make is that your privacy, the way you think about privacy in these models, really has to be tailored to the setting, okay? And what that means is that you sort of have a different privacy model potentially for every setting, and so you have to be very thoughtful about how you write down the requirements of the system if you want them to be meaningful. And so, what this is often called, like, people will often sort of distinguish the thoughtful version of the definition from the first knee-jerk version via a term like person level or user level if you work for a large company, differential privacy. And again, the sort of complication is that individual contributions don't have to align with the sort of locality of the data. And so, like, just to give you, two versions to think about that illustrate this, like, here's one setting to think about. Think about, I'll call this the, like, few hospital setting. We've got a smallish number of data sets. How many hospitals are there? A couple of hundred or something. But each of these data sets is about many people. And potentially each person's, Alice's data may be spread among several of them, right? So that's one type of setting of federated learning. It's not what Google thinks of as federated learning, but it's what many other people think of as federated learning, or among other things. And so in this case, you're sort of, for contrast, we could call this like the many phones model, so, or whatever the devices are, right? And there, each device is really about one user, and so now the correspondence between, one point I forgot to say, in the hospital's case, it's not even clear where Alice is in all these data sets, right? It's not even clear that these are the same Alice, right? If you don't have good unique IDs or stuff like that, it may not be easy to match people up. On the other hand, in the many phones model, it's usually not quite as tricky to figure out that Alice's toaster and Alice's smartwatch belong to the same person. Okay, but whatever. The point is that these entail like completely different algorithmic approaches, completely different modeling and completely different algorithmic approaches. And so there's like an increasing amount of research on this, but just sort of the thing I'd tell you to look out for is when you're reading papers on this or thinking about such a problem yourself, just be think very carefully about the modeling of privacy and whether or not it corresponds to where actual people's data actually lives. So this is one type of issue that comes up. Another, maybe I'll just skip this. Sort of like another type of issue that can come up is I can have a situation where every record is actually about a subset of people, right? So for example, if I take email, a data set of emails or text messages, it might be reasonable to think of the data set as a graph or a hypergraph. And then we might want, then the notion of privacy might look something like what's called node differential privacy, which has been studied a lot for the case of graphs and maybe a little bit for the case of hypergraphs, where I'm sort of two data sets are neighbors if they differ in sort of one person and all of their email, right? And so this is complicated because sort of my data now overlaps with your data. Right? So it's not that they're sort of well-defined. And again, this entails lots of really interesting technical challenges. And in particular, just like a basic idea of a lot of differentially private algorithms is to limit the influence of one person or one individual on a computation. And that gets more complicated when these data, sort of what each person's data is sort of intertwined. And so there's lots of interesting algorithmic problems. And then when I mentioned output structure, again, we sort of have to think carefully about privacy in this setting. And I don't really have time to write down a specific, I have in my slides some specific definitions, but I don't really have time to go into it. But I'll just try and maybe I'll skip ahead a few slides and just give you like one picture. So imagine we've got a bunch of data sets here and some training algorithm that is producing a bunch of models. And in this case, I'm thinking of the training algorithm as centralized for the purpose of privacy modeling, even though in reality it may actually be a distributed computation. And now the kind of thing I might need to worry about is that each of these models might necessarily reveal very fine-grained individual information. So like the example I like to think of is labeling, people's faces in photographs. So we all have different people in our photographs. A people labeling model is definitely like revealing private information about me. It has my kids' names in it and stuff like that. And so you can't really hope for this entire list of outputs to be private. Okay? So the kind of thing you might require instead is something like this, where when I'm defining privacy for a purple person, what I'll think of is I'll think of an adversary who has access to all the other outputs and who knows all the other data sets, right? But now the thing that changes when I change one person's data set, I am getting a different data set, purple data set. I'm ignoring the fact that the purple classifier has to change completely, so I'm not even going to look at it because it is supposed to change. But what I want to say is that the set of other things should remain the same. Right? And so as you can imagine, just sort of writing down the requirements carefully already takes a little bit of thought. We have this paper that appeared last year that has some like outlining some of these models. These use a concept called joint differential privacy that dates back to the 2008, 2009, 2010. But in any case, I don't have time to go over it. Okay, so I just wanted to say that these things exist. There's sort of lots of algorithmic questions that come up, and lots of interesting open questions, both theoretical and practical, about how to make this work. Okay, but to a first approximation, it's a different research question for every scenario you kind of write down, which is both frustrating and fun, depending on if you care about building systems that work or writing papers. Okay, so what changes? Like input changes, output changes. The other big thing that changes is that we're now typically running in some sort of distributed architecture, and so that creates a much larger surface area for attacks. So very often, my generally preferred way to think about it is to first do modeling and algorithm design in a setting where there's a central data set available, and then separately think about how to distribute the computation. But that may or may not always be feasible, and that's something that Adria is going to talk about after the coffee break. Maybe I'll just end up, part 6, that's shorter than everything else so far. It's just one slide. The 40-minute version will wait. But just some questions about, first of all, there's tons of stuff we didn't cover in the tutorial, but I think maybe more critically, there are lots of questions we're not asking in the literature and in the research community. And this is not an accusation. I mean, I think most people who've worked on this are aware of these questions. They're just hard, and they're less easy to tackle. It's often not as obvious how to tackle them. So one sort of big kind of ongoing question is we've got these privacy parameters like epsilon and delta, but a dirty secret of most implementations is that we end up using, to get good results, we end up using settings of the privacy parameters that, taken at face value, aren't very meaningful. Okay. Now, that doesn't mean that these systems aren't providing an interesting and strong guarantee. It's that we don't have a great language for capturing what it is. Maybe. I mean, maybe they're terrible, but I don't think that's the case. I actually think it's generally the case that they're pretty good and they're thoughtfully engineered and they've been poked and prodded enough by thoughtful people that there are no obvious attacks most of the time.
When did you say value is there, but the guarantee itself is meaningless.
That's right. So like, for example, let's say I take a system with epsilon equals 20, okay? So there exist differentially private algorithms in which if you set epsilon equal to 20, they are noiselessly publishing everybody's data, right? Now, if you run DPSGD with epsilon equals 20 for millions of steps on, on interesting data where the norms vary and all sorts of complicated stuff goes on, are you getting an algorithm that's noiselessly publishing people's data? No, you're not, right? And to some extent, this is just a matter of tightening the screws and coming up with better analysis techniques and better algorithmic techniques. But there's a sense that there's more going on here than that, and that we just don't have a great language for capturing, that the sort of current language we have is it's somehow too coarse or not quite adjusted right to capture what's going on in these systems, and that there's something interesting to say there that isn't, I mean, in addition to the sort of straightforward technical questions of just like getting better accuracy at a given epsilon or something like that. Yeah, Adria.
So, why do you think there's something interesting to say there? I'm like.
Because I'm an optimist.
No,
I'm
I'm thinking a unit of privacy leakage, right, is context dependent, right? So, losing an epsilon in a given context is different from losing an epsilon in a different context, and that seems to be unavoidable. Is this not what we are discussing? Why is this not inherent to differential privacy, that epsilon in different contexts are different and we have to live with it?
So I think, like, one answer to the question, I'm sure there are many answers to the question. One is that DP has this, implies a very worst case modeling of the adversary's knowledge of the data set, right? I know adversary knows n-1 data points, has 2 values for the remaining person, right? It's unusual that that would be a realistic threat model per se. What is a kind of remarkable success of the field, I think, is that there are many like basic, really nice settings, like mean estimation that I was discussing earlier, where this kind of super worst case modeling is actually like butting tightly up against settings where very much weaker seeming attacks actually work, and that there's sort of there's this kind of nice threshold-ish flavor to these results. But those settings are somewhat exceptional, right? And they tend to be somewhat stylized and nice because they allow for, like, that's why we understand them. There's, I think for these sort of more complex algorithmic settings, like just DPSGD, it seems to be that we get a much stronger privacy guarantee by releasing only the final iterate of DPSGD. There are good reasons. We understand various barriers to like extending to tightening the analysis we have for those algorithms. Not least, like one, just as a simple example, a lot of the analysis we can do is for convex settings, and those aren't the optimization landscapes we face in these kind of many real life scenarios. Okay, I'll try and be brief. So privacy has many dimensions. I sort of talked about this earlier, but there's a lot. Privacy is a human concept. It's a natural language concept. It means many different things. It sort of means control over your data. It means sort of like there can be like context dependent settings where like certain types of leakage are different from other types of leakage. I don't really care if everybody learns that I was wearing a blue shirt today, right? But there, other things I do care more about. And so, so I think there's sort of still lots to be thoughtfully said about this topic. There's also this issue that I mentioned earlier that sometimes aggregated information itself, sometimes this distinction between sensitive and aggregate doesn't really make sense. Sometimes the aggregate information is the problem. And this often gets into how we use the information that's being released is going to be used, right? So privacy is a weird concept. It's It is in many ways about sort of protecting myself against future adversarial interactions with the world. And so like how you think about privacy really should sort of should incorporate some thinking about what's going on downstream, but concepts like differential privacy don't have the granularity to do that. And then there's like maybe I hope this will come up tomorrow a little bit, but there's also this sort of network effects and sort of strategic considerations that come in from that. So Katrina actually has a really nice CACM article that highlights some of these, some of these points. But to like just make 2 points. One is like, I don't entirely control my privacy. Even if I control how my data gets used, I don't really control how other people use and broadcast information they know about me. And the fact that their information is somewhat, to some extent, about me. Like we live in this highly networked world, and it's often very difficult to tease apart what is only about me. But then there's also the fact that like if everybody else is on TikTok or Instagram and signs up to give away all their information, then maybe I have no rational reason to not do the same thing, right? And there's this kind of sort of a privacy prisoner's dilemma effect that goes on with these sort of systems where, like, I may, there's lots of studies on how people, real people think about privacy, but like a big one, one of the effects that goes on is like, well, I may not have the choice if I want to play the same game everybody else is playing, but to give away my information or to sign up for the invasive system or whatever it is. Like even though in theory I kind of can make these choices individually, in practice the network effects make that hard. And so they're really interesting questions of how one breaks out of those types of equilibria, if you will. If that's indeed what we want to do, or maybe the cost of these, maybe the benefit of these equilibria is such that we don't want to do that. I would tend to think of them as bad equilibria, but whatever. So, so anyway, lots of things that I think are, like 25 years ago, the sort of types of questions we started this workshop with were as vague as these. And people were like, why do you even think that has a shot, you have a shot of formalizing this? And of course the answer was, well, I don't know, like, I don't have anything better to do, I might as well try, right? So, I don't see any reason why we can't chip off at least meaningful chunks of these problems, or tease them. Of course, each of one of these is many problems, it's not just one problem. And again, I'm an optimist about these kinds of things and the sort of the value we can get out of trying to tease these apart and trying to sort of think more precisely about them. Okay, so that's all I wanted to say. We should stop there so that Adria has some time. Do we want to start at 20 to the hour? Is that, or maybe let's pretend we're going to start at 3:35. Right? It's 3:20 now.
Do you need more than 15 minutes?
Do we really need more than 15 minutes to drink a cup of coffee? No. Right. So 3:35. Adria is on. All right. Thank you.